Hello, my name is Connie, and I'm going to be presenting model discovery of origami-tensegrity structures for my final project. So space robotics are often lightweight and adaptable robotic systems, which are useful specifically because space missions often have strict mass and volume constraints. So people have looked at origami-inspired designs where they're flat foldable. People have also looked at tensegrity-inspired designs, which are actuated by cables. And so, of course, people are also looking at origami and tensegrity designs, which is basically cable-actuated origami. These designs kind of combine this origami and tensegrity structure, which allow us to tune the shape and the stiffness through the tensioning of the cables and also create these modular robotic mechanisms. So how can we create constitutive models for these modules? And also how does the model change with applied pretension? So Oshalik et al. Tested the force displacement curves on an instron of two pretension levels of one of these modules at 3 newtons and 5 newtons. The experimental setup used a steel plate to apply an axial load on the instron, and the load cell was used to measure the inline cable tension of the internal cables. And on the right, I have the force displacement curves, the blue indicating the 4.5 Newton pretension and the 3 Newton pretension in red. So our model architecture is very similar to the brain can. It's a constitutive network implemented in TensorFlow with two invariants, two polynomials, and three activation functions, because we believe that this behavior of the mechanism is dominated by elastic geometry deformations and also cable tensions. So this makes sense as a model architecture choice. Assumptions, we assumed hyperelastic response under loading. We also assumed that this is quasi-static behavior, which is reasonable for an instron. And also the reference configuration has zero energy with no loading. And we also assume that this origami tensegrity module can be captured as an effective material. So here are the fitted curves for the 4.5 Newton pretension case. As you can see, the model does better when it's less sparse for the blue curves. However, for the red curves, the model does better when it's more linear, indicating the more linear response for less pretension at 3 newtons. Um, as expected, the less L1 regularization lambda parameter means there's more active terms, and less pretension seems to be easier to model, with the 3 newtons being much more linear in response, indicating that higher pretension means there's more complex coupling of tension and plate bending mechanics. So overall, this doesn't incorporate the structural parameters such as cable stiffness and plate stiffness or pretension, which could give the network more information. So our future work will focus on that. Thank you.